Are we ready? Right. Hi, everybody. Welcome. And let's see how it goes. I'm using a new machine, a Microsoft Surface. I've only been handling it for 5 minutes, so let's see how it goes. If anything goes wrong, we'll try and sort it out. Right. I'm going to open the formal lecturing on my half of the course, which runs in parallel with Tatiana's. And as I said last week, I'm interested in heuristics, learning systems and neural networks, and also next time we'll be looking at image pre-processing, which hopefully will make the job earlier. Now, the key things we're looking for are self-evolving systems. So self-evolving is a key property. We want no analysis. The system should do the analysis for you, and we want no human intervention. Whoops, getting used to this. That really is the keys to an intelligent system. Now let's look at a traditional way of doing analysis.
This is going to be the other side. Kitata's the only one who responds, or it's Kenyon who's just forging ahead. Not by much though, it's only half a meter. Neck and neck, stride for stride.
Somebody's listening to horse racing.
The two of them, nobody giving either.
Steven, we appreciate you absolutely love horse racing now. Unfortunately, we are doing the horse racing in intelligent systems at the moment.
Right, traditional analysis. We start off with data from the real world. Sounds, noise, pictures, smells, whatever. Measurements. You have a hypothesis. How do all the measurements fit together? And from that hypothesis, you try and get a model. You test the model. And if the model is found inadequate, you revise your hypothesis. So research really is in this area here, going around this loop. And if you're very lucky, you're tackling a new problem, you have the hypothesis, you get the model, you test it, and it works first time. Success. Other more difficult problems, you might go around that loop many more times. Some problems which don't yet have a solution, maybe will never come out of the loop. But somebody like Newton 300 years ago with his dynamics, he came out of the loop and he had equations. And once you have equations, I'm thinking of his equations of motion, then you can solve problems. And from the equations, you can get software these days. You can get systems, you can get products, and you get money. So that's a real success. Whoops, go up. We'll come here. Loads of money. Right. A learning system is completely different. And a learning system is some processor which receives data from the real world and it receives the answers from the real world. And in this system, we hope a mapping or a set of equations, a function might emerge. Now, the sort of situation where that might occur, take a very young child and you are showing it a picture of a cat. That would be the data. The answer is cat. And somehow that human, that young human, makes a link and develops a function which will map the image of cat to the name cat. So that's the sort of situation we have. That is the training of the system. Now, when we come to use the system, we've got our functions. The data comes in and the answer will come out. Now, the key thing to note at this point of time is that the data going into the testing phase is going to be different from the data going into the training phase. And we saw last week the huge amounts of data that can occur with images. Just to remind you on that, a single pixel, if it's 1-bit coding, 2 pictures. If it's 2 pixels, we have 4 pictures. If it's 3 pixels, 8 pictures. N pixels, 2 to the n different images. And to take it to an image which is barely recognizable in quality, a 16 by 16 image, then the total path, let's call it U, is going to be total number of pixels. 16 by 16 is 256. It is 2 to the 256. 2 to the 256, I approximate, is 10 to the 80. And 10 to the 80 is that huge and interesting number, supposedly the number of fundamental particles in the universe. So a very strange fact. If we were to try and print out all patterns on a 16 by 16 array, 1-bit coding, terrible low resolution compared to what your phone is. But if we tried to print out all those patterns, there wouldn't be enough matter in the world to actually print them, because it sees the number of fundamental particles. So the data going back to our learning system, the data coming in on testing is going to be different.
Okay, got it. Join. we need to wait. Okay, and share. Here's our whiteboard. Yeah, going. Let's see.
Right, I'll be back.
Let me check if I can transmit this whiteboard. You cannot see the whiteboard. Here's whiteboard. Yeah. Okay.
Right, are we back on?
Yeah. I think you better deliver lectures from me, even if you have also.
Yes. Okay, is anybody out there still?
Yes, we are here. Hello.
Apologies for that delay, the system went down. Right, just to recap where we were. A learning system. Train on data. Apply the answers you require, and the system should evolve some function or mapping that links the data to the answers. Testing, you apply data to the functions derived during training, and you get your answer coming out. Now, the data that you will use on testing will never be exactly the same as the data on training because of this huge data universe and the impossibility of capturing exactly the same data from the real world using cameras and microphones as has occurred in the past. So one interesting thing you might find in research papers is people will produce fantastic results on learning systems, 90, 95, even 100% success on data. And be careful if they're claiming that, because it is unlikely to be correct. It is more likely that they are testing on a data set and they are then evaluating it on the same data set. That does not solve the problem. It does show that we can get a map data of a particular set into the answers, but if the new data coming in is different, then it doesn't necessarily mean the system is working. And this ability to recognize perceptually similar data that is similar to the training set but not exactly the same is this generalization property which the system must have. Right, moving on. Right, let's now get down to some details. The three general methods I want to look at this morning. Method one, let's go to black pen. Method one is heuristics. Now, heuristics is a posh name for rules. I then want to go to method two, which is learning systems. And the third part of this course will be neural networks. So those are the headings for the next month or so. Starting off with heuristics. A simple heuristic could be if it looks like a duck and quacks like a duck, then it is a duck. Now that is a very simple thing for a human person to implement, but you try and implement that in a machine without any human intervention. It looks like a duck. That's pattern recognition. You've got to recognize patterns which are ducks. It sounds like a duck. You've got to do sound recognition.
Writing is not clear.
What do I do about that?
Write bigger.
Write bigger.
Or clearer. Is it your writing like this? No, you're writing normal?
My writing is pretty bad, yes.
So wait,
Let's have it flat.
it's like flat. Try this one.
Right, okay, let's carry on. So a heuristic is a simple rule. Now I want to start off with a mathematical rule, which is shape factor. Now shape factor is a mathematical equation, a very simple one. It relates perimeter to and area to the shape factor, and it is defined as S. So the shape factor S is the perimeter squared over the area. So P is perimeter, and A is area. Perimeter, yes. So hire a mathematician and let's analyze a circle. Incidentally, the shape factor is sometimes called compactness. And for compact two-dimensional shapes, what is the most compact two-dimensional shape that we can define? It's a circle. 3 dimensions, it will be a sphere. And a good example of that is the Earth. It's floating in space. There's gravitational pull within the Earth, and the whole thing condenses to a sphere. If we go beyond 3 dimensions, it becomes a hypersphere, which is difficult to imagine, but exists. So let's take a circle in 2 dimensions. And we go to the mathematician, and he or she will tell you S is going to be the perimeter, which is 2 pi r, all squared, divided by the area, which is pi r squared. And we can expand that. That is going to be 4 pi squared r squared divided by pi r squared. And I hope your mathematics from the early days will enable you to simplify that. Whoops, what's happened there? Lost my screen. Right. The r's. Right. The r's will cancel. Let's change color. And one of the pi's will cancel, which will give you a shape factor for a circle as 4 pi. Hey, that's a number. It equals 13.4 approximately, if you work it out. And it is size independent. The size parameter r has cancelled out. That means every circle have a shape factor, SF, is going to be equal to 4 pi, a constant. There's your generalization. You don't have to specify the size of the circle. Any shape which is a circle, if its shape factor is 4 pi, it is a circle. That is a rule which we could use for recognizing metal shapes. Let's take another example. Let's take a square. And let's have sides D. Well, I'll give you 20 seconds to work out the shape factor for a square. Perimeter squared divided by area. Any answers coming up? Writing is very unclear. Do try and do my best. Can't quack underwater. Yes, you can. It's just a different noise. It's called sonar. Write clearer. Do my best. Any answers for the square shape factor? Perimeter, 1, 2, 3, 4 sides of D. Perimeter is 4D. Perimeter squared is 4D all squared. Area is D squared. 16D squared over D squared. Again, the size disappears. We can cancel the size, and a square has a shape factor of S equals 16. Any square. And as an exercise, you can take other mathematical shapes and see what the square factor is. As the shape gets more distributed, the shape factor will get larger. Right. Now, let's remove mathematics from the shape and see if we can obtain this perimeter and area using image operations. So first of all, let's define our image format. And traditionally, an image, we regard it as a two-dimensional picture. This originates from old-fashioned television, where a picture was scanned with an electronic beam scan, and it always started from the top left. This dimension, and this is the J, so the I's are the column index, and whoops, where's that ruler come from? And the J is the row index. And the image is made up of pixels. I will draw one square, and that will be P row I column J. Right, now let's move to let's take the square because it's easy to draw. Square shape factor using image processing. And the square, I will draw a pixel image, low resolution. I will use a 5 by 5 array. And although one would be applying this to megapixel images, when it comes to exam questions, if we indeed have an exam at the end of this year, then typical examples and tests will be on low resolution images, so you can calculate them in an exam. So that's a 5 by 5 image. And let me put a square on that. And the square is going to be this region here. So there is my square. Now we need S equals P squared over A. Let's start off with the area A. Given the image array in the computer, you can get a measure of the area as the summation over all I and J of the pixels Pij. And we can count that up on this simple image. It is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 pixels. So in terms of pixel areas, A is going to be equal to 9. Right, we now need the perimeter. And for the perimeter, we need to count the pixels on the edge. So taking the same image, if I apply an edge detection algorithm, which we'll look at later on in the course, but let's assume we know what it is and we can use one. If I did an edge detection algorithm on the previous image, I would want to detect all the pixels that are on the edge, but not the pixels that are within the image. In this case, the pixels on the edge are going to be there we are. That is an edged square. The only pixel that has disappeared is the center pixel. If we now calculate the perimeter, we can have the perimeter as the summation over all Ij of the edged image. And let's call that Pij. And let's put an E there, indicating edged image. Calculating these 1, 2, 3, 4, 5, 6, 7, 8. So P is going to be 8, which for that shape factor for a square, S is going to be P squared over A. It is going to be 8 squared over 9. 64 over 9, and when I calculated last time, it was about 7.1. Any comments on that? Something is seriously wrong. We started off with the ideal square, which was 16. We know that the shape factor for the most compact shape, the lowest possible value, is 13.4. And what we are getting with this simple example using image processors rather than mathematics, we are getting a shape factor of 9, far too low. What's the problem? Well, the area is likely to be correct, the summation of the pixels in the original image, but it is this perimeter.
9 is the area, perimeter is 12.
No, we are counting pixels. We are not measuring edges. All you can do on the array is count the ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember that image, to you as a human, it looks like a square, but that image is going to be 0, 0, 0 in the top row. It is going to be 0, 1, 1, 1, 0. And all you can do to calculate the perimeter from the image, the perimeter must be 1, 2, 3, 4, 5, 6, 7, 8. And of course, it's wrong. And the problem is in calculating the ones here, we don't know whether these ones are corner images or part of a line. So this pixel in the middle here, let's put a yellow mark on it, or green. That pixel is 1, but this pixel is 2 edge units. So we have a resolution problem. And if we try and do these techniques at very low resolution, we find that the errors are huge on the perimeter calculation. If I now take that to a higher resolution, the higher resolution, let's say 1000 by 1000, the area is going to be, if I calculate, if it's all black, the area is going to be 10 to the 6. The perimeter is going to be, there's going to be 1000 pixels on the top row. There's going to be 1000 on the bottom, but there's only going to be 998 on the columns because I've calculated that pixel in the top row. I will have 998 and 998 there. So the total perimeter is going to be 1000 plus 1000 plus 998 plus 998, which I think is equal to 3996. If I now calculate the shape factor, S is going to be P squared, which is going to be 3996 over A, which is 10 to the 6. And I think when I calculated that out last time, it turned out to be 15.96, which within experimental measures is close to the theoretical value of 16. So using shape factor, we've got to use high resolution images.
Now you have a question. Won't it be? Yeah, this will be 396.
You're quite right. Thank you. The square. Good spotting. Right. Have you noticed something about these images? I have chosen them to line up exactly with the pixel array. When you're pointing a camera at the square, that is certainly not going to happen. So, like all techniques, there are problems. And let me take a 3x3 image again. There is the array. If I place the image, and there is my shape, if I place that on the array, then I would get a shape. It goes in red. Oh, gone, it's gone. Oh, Tatiana, lost it. Ah. I would get a shape in there, which is well behaved. If, however, I put this shape in this, on the array, drawing it fairly accurately, I am going to get a shape that looks like this. Let's wind it in. Keeping it square. Now there the object doesn't fit exactly with the pixels. Which pixels are going to be black and which pixels are going to be white? We have to apply a threshold. This clearly is going to be 0. This one is clearly going to. But what about this one? It's about 40% of the pixel covered. And there will be a threshold at which the cell, if it's digitized, will be 0 or 1. And it can vary, and it can vary between the CCD characteristics on the array. So we've got a noise. At the very worst case, if I took an image where any pixel that has a part of the object in it is going to be 1, any pixel that doesn't have a part is going to be 0, we would get 0, 1, 1, 1, 1, 1, 1, 1, 0. If I only took the images where this is, if you like, t equals 0, if I then took t equals 1, i.e. total cover of the pixel, the image would be, in fact, there's only one pixel that's completely covered, it would just be the center one. Depending on the threshold, we are going to get varying, very different images. Now, this is worse at low resolution. The problem does become less at higher resolution, but we have this problem: edges are always noisy, and that will give variations in data that you don't expect. The other issue on resolution is a more fundamental one. If I am counting pixels for distance, supposing I was counting this distance as a perimeter, if I'd edged this image, the center pixel would go to 0, I'd be left outside, and going from here to here, I would count that as 2 pixels of perimeter. But if I'm counting on a pixel, take a single pixel, then if this is distance d moving horizontally, if this is distance d moving vertically, counting pixels moving diagonally will be a distance d. It's 1 pixel, that's all we can measure. But the true distance there is going to be root 2d. And we would just count that as 1 move in the diagonal direction. Now this is going to be 1.4d. It's a 4% error in measuring distances on a diagonal move on an array. And sadly, there is no solution to that. One cannot increase the resolution to reduce that error because it's a fundamental geometry within the pixel. Whatever the resolution, if you are measuring distances diagonally, you have a 40% error. So with this simple idea of compactness, looking at shapes using image processing techniques, we are seeing problems. What started off as a very simple problem is becoming much more tricky. Now, we are still dealing with known shapes, geometrically regular shapes, which the mathematicians can give us formula for area and perimeter. In industry, and I have two examples in mind, clothing manufacturing and shoe manufacturing, where two-dimensional shapes which are irregular are being used and might need to be sorted. If I take a shape which is arbitrary, like that, the mathematician cannot give you a formula for the area. The mathematician cannot give you a formula for the perimeter. It's an irregular shape. And to get the area, what the mathematician would do would be take smaller and smaller segments and add them up, essentially counting pixels. And the same would apply for the perimeter. The resolution depends on the sample size. Certainly with the perimeter, the higher the resolution, the more accurate the perimeter becomes. And an example of where small samples give better results, if you were to measure the coastline of the UK, the island of the, what's it look, something like this, there's the Cornwall, there's Wales coming out there, and there's Scotland up there, something like that. If that is the UK, an irregular shape, if I took a pair of dividers and I was taking 1 kilometre samples, the measures I would be taking that point there, to that point there, to that point there, the image would be like that. If, however, I took a 1 metre sample, stepping round, it would be much finer steps, and I would be measuring the perimeter in much more detail, and it would be more accurate. So with irregular shapes, the higher the resolution, the more accurate the shape factor becomes. So does this have any practical use? Well, yes, it does. The idea of components for shoes, I mentioned this could be a piece of leather on the side of your shoe. For a limited set of examples, you can use the shape factor using image calculations to sort shapes. Okay, there will be a range of parts and there will be a limited number of categories. And I've now lost my picture again. Tatiana.
Oh, come on. This is messy. Well, interesting time. Be with us, please. We are trying to resolve the problems. Completely dead. Yeah. Okay. Give us a second, please. Join. Podcast. Okay, we're trying to reanimate. Be with us, please, because it doesn't go everything smoothly. Come on. Get this one. I don't want to put him in freezer at the moment. I'm trying to put this down. Okay, be with us, please. Apologies for this. I'm trying to solve this problem as quick as possible. Okay, this one doesn't start. Let's have a look. Yep. So it cannot survive 1 hour lecture. We need to make sure we plug in all the time. See, it dies. No, it's but the 5 with scarce is a cast. Okay, join. Rejoin. Now let's see. Okay, wait a second. I will stop sharing here and let me just remove this part. Stop broadcast. Join. Join. Okay.
Right. Are we back again? I hope you're still there, folks. Sorry about this. Right.
Yes, we are merged dragons.
So that's the basic outline of shape factor, a very simple mathematical technique, but when you try and apply it without human intervention, it becomes a lot of problems emerge. The other thing is, I suppose shape factor is too good to be true. It's a single measurement. Can it possibly recognize and have different values for all different shapes? And the answer is no. And I will leave you with a problem to look at in your own time. Supposing we're applying shape factor to character recognition, and I have two examples of characters, and we'll stick to very simple 3x3 pixel resolution. And let's have a typical letter L. There is a 3x3 L, and there is a 3x3 T. Two very different shapes. Now apply shape factors to these two characters. Because it's so low resolution, use geometry. Calculate the perimeter, the exact perimeter, by looking at the images and the exact area. And if you apply the shape factor to the L and you apply the shape factor to the T, you will find they have the same shape factor. So not all shapes have unique shape factors. Just to give you the L, the area in terms of pixels would be 1, 2, 3, 4, 5, and the perimeter would be 1 there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for the L, A is equal to 5 and P is equal to. Apply the same to the T and you should find that they have the same factor, shape factor. So it won't work on character recognition. Very simple strategy, but we've discovered problems with it. Let's look at some other coding representations. and I want to look at a run code.
Okay, we can't see cursor when you look with.
Problem?
They cannot see the cursor unless you write on the way. So basically, you need to, when you describe this, you need to
Wait.
either to wait or do the second line so we can see what you're describing in.
Okay, I'm going too fast, my usual failing. Right, a run code. Let's have a full sheet of paper. It is image compression. And let's take a irregular shape on an array and assume I've drawn it as an edge, but assume it is a solid area. In fact, I'll shade it in. Now with a run code, you start scanning the image from the origin. There is the origin. And scanning row by row, detect the first row in which part of the image occurs. This is the first run, and it will be between the axis and the first pixel of the image. And we label this run W1, the first white run of the first row. So it will be W11. We then measure the next run. We measure the next run, which will be B, the first black run of the first row, B11. We then, for the remainder, measure the next white run, which will be W, the first row, the second white run. So the index is the row and the run within the row. One then goes to the second scan, and I'll draw it rather coarsely down there. There will be the second run. This will be W2, the first run, white run of that row. Then we have a black run, which will be B, the second row, the first black run. And finally, the second row, the second white run. And from that, we will get a series of numbers which represent the constant runs of the image, and it gives you image compression. And this idea of storing a run of constant values is a very common technique in image compression. So let's go backwards for an example which might make it clearer. A typical run code. For a 5x5 image. And supposing the run code, let's call it a pattern X, equals 3, 1, 1, 2, 2, 1, 1, 4, 0, 2, 3. It's a series, a list of numbers. It is a 5x5 image, so 5 pixels per row. We can immediately segment this into rows because when the numbers add up to 5, it's a complete row. So putting in the row segmentation, 3, 4, 5. And 0, 2, 3, 5 is the.
Sorry, it's me. Sorry. Apologies, it's me. I was trying to experiment. Oh my God. Apologies. Where is it? Right here. Oh, come on. It's very slow. Sorry, I promise I don't experiment anymore during lecture.
Right, you're back online. So we've segmented the run code into rows because we know it's a 5 by 5 image and we are expecting 5 pixels in each row. This 3 here would be the first white run of the first row of the image. So going back to an array, there is the first row. It will have 5 pixels in it. 1, 2, 3, 4, 5. The first row is a white run. 3, 1, 2, 3. This is the first black run. It will be a black pixel there. And the second white run of that row. Now the second row, a white run of 2, a black run of 2, and a white run of 1. Now the third row is going to be a white run of 1 and a black run of 4. Now for the last row, note the white run is 0. You have to include that 0 in there, otherwise if we started with this is a black run, it will be interpreted as white. So if no white run first in row. Oh, this writing is awful. Then WN1 equals 0. No white run, we have a black run, first of all, which would be your 2 there. So that 2 becomes those 2 pixels there, and the 3 are white. And that will then give you your run code for that image. Now to check it out, an exercise for you, convert it back to its run code. And if you do that, you should get the answer to start off with. Okay, what's the point of this? Well, it's used in industry, an application. One application I've seen is bottle inspection in manufacturing. The run code doesn't have to be horizontal, it could be vertical. So we have bottles coming along on a conveyor belt. There is a bottle, you would do the run code in that direction. You would end up with a vector. That is a match to a perfect bottle. Then we get another bottle coming along with the neck broken. That will give a different run code and a means of detecting from the image of the bottle that is no good, that is okay. And at this point in time, I think I better finish because I've overrun. It's been a bit of a difficult session, but I hope you've got something out of it. The key things are the shape factor. The mathematics is perfect for shape factors for regular shapes. When we apply them to irregular shapes, it doesn't work particularly well. We have noise on digitization. We can get shape factors, but they are not consistent. They are not variable. It's a means of working with limited classes, limited categories in shapes in manufacturing. The run code, it gives image compression, and matching the run codes can be used for inspection purposes.
Okay, you have a question.
A question.
Does a run code have to happen by scanning each row one?
No, you can do it simultaneously if you want parallel processing. What other questions have we got?
No,
Looks
just
like
this one.
Oh, sorry about Northern Ireland, Ollie. Yes, let's put Northern Ireland back on there. Oh, I've lost it now.
Go don't know.
Uh, okay. Okay, there's Northern Ireland. But it's not a separate image, so it's different country, different shape. Got to see between them. So there's two shapes there. Right, what else are you saying? It's on Blackboard Collaborate. I hope it is. Oh, Ireland, the whole of Ireland. Yes. Oh, must be politically correct. The whole of Ireland. Yes.
26 plus 6 equal 1.
26 plus 6 equals 1. What's that?
Can you please kindly send us email about points? No, you have a recorded version of a lecture. I will send you the copy of the screenshots. We will expect you that during the lectures you do take some notes by yourself. You are not relying on us providing you lecture notes.
Yes, in your own time, try some shape factor examples, calculating them from pixelated images, and try some run codes. Convert run code back to image, image to run code, and do some sorting of circles and squares with shape factors. But don't apply the mathematics. The key is to operate on the images, because that's what intelligent systems will do. They won't have a human there detecting corners. Okay, that's me finished.
We will gradually start to improve, and we are learning our bits and pieces.
Right.
And we will see you on this Thursday coming up. So basically, again, Teams, and we will let you know how it goes. See you guys. Bye.
Bye-bye.